good afternoon to everybody. It is my pleasure to introduce our last speaker, Professor Markus Luty, who is a faculty member at the University of California in Davis since 2007. Markus' research interests are very broad, and they involve topics in particle phenomenology, particle cosmology, and also more formal issues in quantum field theory. Concerning the subject of his talk today, he has been playing a prominent role in the last decades in the formulations of new theories for the Fermi scale, so as extensions on the Standard Model, in particular, new mechanisms for supersymmetry breaking. He was the co-author of one of the few papers that discover anomaly mediation, but also theories with extra dimensions and new strong dynamics at the weak scale. Besides physics at the weak scale and collider phenomenology, Markus has been very, very active also on issues more related to astroparticle and cosmology, such as dark matter theories, models to generate the baryon symmetry, solutions to the cosmological constant problem, and infrared modification of Einstein theory of general relativity. Last but not least, as I mentioned, he gave also important contributions to formal issues in quantum field theory. And one striking example is a famous paper where he gave a generalization of the proof of the A theorem in quantum field theory. Today, he will tell us about what to look for in the future. The title of his talk is The Higgs Boson, A Tale of the Two Universes. We will follow a scheme very similar to the previous one. So in case there is any urgent question, perhaps can be written in the chat, but otherwise we have a Q&A at the end with Markus about this talk, and then a general discussion with all the speakers of today's event. So Markus, it is great to see you, even though only on the screen, and thank you very much for having accepted our invitation, and feel free to begin whenever you like.
Thank you very much, Francesco. It's actually quite humbling to be here, and especially there's some of the true pioneers here in the audience, and I will do my best. Oh dear. Okay. All right, now I'm not able to advance.
Markus, try to click on the slide with the mouse.
Okay, that works.
Okay.
All right, but let me just see. Okay, all right, now it works. Okay, very good. Okay, so I am going to be taking a much more view. I'm going to be covering some of the same ground that John Ellis very nicely covered in his talk, but I'm going to be taking a much more sort of a historical view of history, the view in hindsight, the view of how do we understand things in retrospect, okay? But I think that's also very important to set up the discussion of how do we look towards the future. And I have to say, this is my personal view, and also I've taken a slice through the subject to make it manageable. There's obviously so much more that I could have talked about. But the key thing I want to say is that that the Higgs boson truly does play an incredibly central role in the most fundamental questions that I think that we have a hope of addressing scientifically. And that's going to be the main message of this talk. Okay. But first, I just want to say something personal. This is very personal to me. You know, it is just amazing to see all the work that went into the discovery of the Higgs boson over so many decades, experimental, theoretical, people working together. And in fact, it's interesting to me that one of the classic papers by Peter Higgs was submitted just 2 weeks before my birthday. So this is sort of also the idea that I would have been spending a good fraction of my time pondering these mysteries is something that's quite personal to me. So the lens through which I'm going to be talking about things is can roughly be described, goes under the catchphrase of effective theories. And the way I look at philosophically look at theories is that they are simply tools, right? They are something that we use to help us understand nature. And there are two kinds of theories. I mean, there are really things in between, but there are sort of two extremes or limiting cases of theories, both of which I think are incredibly important. The first are effective or phenomenological theories, and then the second is what I call aspirational theories. So effective theories are theories that include only the observed particles and interactions, things that you've already seen, and they're very much driven by experimental data. In fact, they often are attempts to summarize the experimental data in the form of a theory. On the other hand, we also need to go beyond, this is sort of very Francis Baconian, right? The effective theories, but it's also crucial to go beyond that and what I call aspirational theories. These are theories that often include unobserved degrees of freedom or interactions. They're motivated by theoretical principles. We're trying to understand the principles behind the physics. And so we sometimes that sometimes forces us to incorporate things that we haven't seen yet, right? It's important that they are compatible with the experimental data, of course, otherwise it's kind of a waste of time. And they generally will make predictions beyond what's currently observed. And if we're really lucky, we can observe some of those, right? And one of the key themes of what I'm going to be talking about is that, in fact, the Standard Model started off very, very much as an aspirational theory. It was a theory based on grand principles and ideas. And with the discovery of the Higgs boson just in 2012, it became, in fact, the effective phenomenological theory that describes our universe. It's quite a remarkable story, but I think it's important to keep these two kinds of things separate to understand the significance of what was achieved. So let's do a little bit of this ahistorical history. So the earliest theory of weak interactions proposed, well, anyway, Fermi's theory of weak interactions came in 1932. It was very, very much in this effective field theory spirit, even though those buzzwords were not in use at the time. So, for example, we see neutrons decay. Fine, Fermi said, we'll just put a term in our Lagrangian that directly has the neutron decaying as we see it doing. And then that Lagrangian can be thought of as a summary of the experimental results, and it can be a basis for further exploration, right, as it very fruitfully was. Now, it was known at the very, very beginning of Fermi theory that this theory could not possibly be complete. And the reason was very simple. If you put in these point-like interactions to explain these decays, then the scattering amplitudes at very high energies, which have not been observed, but you could extrapolate and you could see that they broke down at an energy scale of about 1 TeV. So in 1930s, we knew that the 1 TeV was a potentially interesting scale in the weak interactions because the theory of the 1930s broke down at that scale, okay? And I think this is an amusing slide. Fermi was very aware that the TeV scale was an interesting scale. He thought about what it would take to build a 1 TeV collider, okay, except it was a fixed target experiment and he underestimated magnet technology. So he thought you needed a collider to go around the world to get a center of mass collision energy of a TeV. Okay, fortunately, this was one of the few cases where Fermi was wrong about an order of magnitude estimate. Okay, in the 1960s, people said, well, we have to do better. We must do better than this phenomenological theory of Fermi. So instead of having this point-like interaction, let's introduce intermediate vector bosons, spin-1 particles that mediate the force. This didn't take a huge amount of, well, okay, this was a natural guess because other forces were mediated in this way. And in this way, you could hope that, well, instead of having this nasty growing behavior, you might have something more reasonable, okay? And of course, this theory reduces to the Fermi theory at low energies. But guess what? This theory has exactly the same issue, but with a different scattering process. Now, if you scatter these intermediate vector bosons, you can choose their couplings however you like. You can choose them to make the best high energy behavior that you possibly can. You find that it grows energy quadratically, and the theory breaks down at guess what scale? 1 TeV. Okay, and it's not just a numerical accident, it's actually parametrically the same scale. Okay, in terms of the parameters, okay? And so So from this, we understand that you can't just have the intermediate vector bosons, you need additional degrees of freedom, okay? So as John Ellis nicely reviewed, this was not the thought process that actually went through. This is the logic as seen in retrospect, okay? That there was there's a rationale, at least in retrospect, for adding these new degrees of freedom, okay? And so let me just explain. I'd like to try and explain a little bit about where does this growing energy behavior come from, because that will actually help me explain in terms of basic physical principles, okay? So let's start with a massless spin 1 particle. For example, the photon is such a particle. And if we just take what we know from Lorentz invariance and quantum mechanics, okay, then then a photon is a particle that, of course, can only move at the speed of light, and its spin is parameterized by its helicity, which is the component of the spin along the direction of motion. And if all we had was Lorentz invariance in quantum mechanics, then you could include only the states with helicity +1, where the spin is pointing along the photon axis, and there's no reason to include the photon with the spin pointing the other way. But if you also include CPT, which actually follows from Lorentz invariance and some other reasonable assumptions, you have to also include the helicity -1 state, okay? So just relativity in quantum mechanics tells you that a massless spin 1 particle has 2 spin states, okay? Helicity +1, helicity -1, nothing else. And these are just exactly in one-to-one correspondence with what you know is the 2 polarizations of an electromagnetic wave, right? There are 2 of those, okay? But now a massive spin 1 particle is a different beast. So the massless spin 1 particle always moves at the speed of light. You can't stop it. You can't go to a frame where it's at rest. But a massive spin 1 particle, you sure can. You can go to a frame where it's at rest. And in that frame, it's just like a non-relativistic spin 1 particle. It has 3 spin states, right? With a z component of angular momentum 1, 0, and -1. Okay, so we see that there's a qualitative difference between massless and massive spin 1 particles. They have different numbers of degrees of freedom, okay? And this is the origin of these growing interactions, okay? So to see this, imagine we take one of these massive vector bosons and we try to make it look like a massless one by giving it a huge boost. So we boost it along the z-axis. So when it's at rest, the 4 momentum looks like this. When we boost it, it becomes more and more like a photon's 4 momentum. So the 4 momentum looks more and more like that of a photon, right? But if we look at the H equals 0 polarization, in other words, we look at the component that has 0 spin along the z-axis, it's described by a polarization vector that points in the z direction. And you can see that because that's what's invariant under rotations under the z direction. That's why this is the H equals 0 polarization, right? And if we give that a large boost, the same calculation tells us that we get a 4 vector that also looks like a light-like 4 vector, okay? But its normalization has this factor of MW down there, okay? So we can just see from Lorentz invariance that the H equals 0 polarization, the extra polarization that's there in a massive spin 1 particle actually has a polarization vector that grows with the momentum. Oh dear, okay. And that's the origin of the growing amplitudes at high energies. And that is why we need new degrees of freedom, and they have to have a mass, again, less than this magic scale of a TeV, okay? And these arguments were elaborated in the 1970s, it became clear that if you built a 1 TeV collider, that there would be essentially a kind of no-lose theorem where you had to discover some kind of new physics, okay? Now, I should say that I forgot to mention that I've been calling this a Higgs sector because so far these arguments don't tell you what the kind of new physics is, okay? So we can call it a Higgs sector if we're being agnostic, okay? What is the minimal Higgs sector? The minimal Higgs sector is what was actually discovered first. It was the first thing that was written down historically, okay? But logically, it comes a bit later. It is that it is a fact, it's an amazing fact, that all the growing amplitudes, there are many others, some others that I haven't talked about, all the possible growing amplitudes that you have can be canceled by just adding a single spin zero particle, which is the Higgs boson. Okay, and this is a definition, this is an alternate definition of the Standard Model, not from the Lagrangian and spontaneous broken gauge invariants and so on. This is an alternative definition of the Standard Model that I think is conceptually quite important, as we'll see. Okay, and the picture that emerges from this is very beautiful. And so if you are a student and you have the privilege to study elementary particle physics, it's a great experience. I still remember the experience of learning about the Standard Model as a graduate student. The Higgs is a scalar field, okay? So it has no Lorentz quantum numbers. It has the remarkable feature that unlike other fields like the electromagnetic field, it costs energy to turn it off. So its potential has this sort of shape where the potential is not minimized when the field is zero, potential is minimized when the field is non-zero. And so the lowest energy state, the vacuum state, is where the Higgs is non-zero. Particle masses arise from interactions with this non-zero background field, right? And the Higgs particle that was discovered in 2012 in this interpretation is a quantum excitation of this Higgs field. So this Higgs field sitting at the bottom has now been shaken by the collisions at the LHC, and it's produced measurable effects that we have now seen, okay? And for the first time in the history of this subject, we have a theory that can be consistently extrapolated to the Planck scale. Okay. Now, of course, this is where this distinction between effective theories and aspirational theories becomes important. As an aspirational theory, the Standard Model was written down in the late 60s, and it became pretty soon clear after that it could be extrapolated all the way up to the Planck scale, but that's clearly very aspirational. With the discovery of the Higgs boson, we actually have a theory which is now the phenomenological theory that describes what we have, the minimal phenomenological theory, and it can be extrapolated all the way to the Planck scale. And this has made a lot of particle physicists, including myself, a bit nervous, right? Because you can ask, could this be the final theory? Could this be it, right? And John Ellis commented on that before, but I think it's very clear that it cannot possibly be the final theory, okay? For one thing, it doesn't explain cosmology, and not just little corners of cosmology, but it doesn't explain the bedrock ingredients in cosmology, such as dark matter, inflation, baryogenesis. These are nowhere to be found in the Standard Model of particle physics, okay? It also has many open conceptual questions, right? That it seems clear if you extrapolate from the progress of particle physics in the past, we should be able to make progress, not just in terms of describing particles, but also understanding conceptual issues, okay? And I want to focus in particular on what's called the hierarchy problem. I'm going to explain what it is, explain why I think it's important, and what it might be telling us as we look forward. Okay. So the Higgs boson is a particle which is unlike any other particle we've seen. It is an elementary spin zero particle, at least as far as we can tell. And the fact that it has spin zero is absolutely crucial, okay? So what it means is that unlike the vector bosons, or unlike the spin one particles that I talked about before, the massive and the massless version of this particle have exactly the same number of degrees of freedom, right? A Higgs at rest has no spin degrees of freedom. If it's moving as close as it wants to the speed of light, or if it's massless at the speed of light, it still has no spin degrees of freedom. There's no difference between the Higgs, a massive and a massless Higgs. And this translates to the fact that very, very generically, if you interact with any other particle, okay, than any other heavy particles, the quantum fluctuations of the heavy particle give additive contributions to the Higgs boson mass. Okay, so if you have some very heavy particle with mass mx, the Higgs mass, boson mass squared, for technical reasons, it's the mass squared that gets additive, is proportional to the mass of this heavy particle, no matter how heavy it is, right? But as I reviewed before, this doesn't happen for particles with spin not equal to 0. In fact, way back in the 1930s, Victor Weisskopf predicted that we would never find an elementary particle of spin 0 for precisely this reason. Okay, so this is an idea that goes back way back, and is one of the reasons why a lot of people were very skeptical, including myself. Up to the eve of the Higgs discovery, I was extremely skeptical that the Higgs would be discovered. Of course, I was wrong. Okay, but anyway, but so this is this additive contribution to the mass does not happen for particles with spin not equal to 0. For example, there's no way to turn a massless spin 1 particle with 2 spin states. Somehow quantum fluctuations cannot turn that into a massive particle that has 3 spin states, right? That just can't happen, all right? 2 is not continuously connected to 3. And so this would appear to require some kind of new physics below the TeV scale. Why TeV scale? Because once again, the scale, if you say, what's the heaviest kind of particle you can have? Well, you could have around a TeV scale. So maybe all of physics ends there. Maybe, string theory comes in or something like that. Or maybe there's some kind of new physical principles that makes the Higgs insensitive to new physics. But whatever it is, it better come in at a TeV, because after that, it's too late. Any other heavy particles will make the problem, much worse. Okay, and I gave you reasons before. You could say, why do we need to have any new particles? I explained, I think, why we believe there have to be new heavy particles in the previous slide. So we're sort of stuck. Now, we should be careful. I believe that one should always be extremely conservative, and ask yourself, wait a minute, before we go off and start inventing new physical principles at the TeV scale, are we really sure that we have to have something there at all? Because after all, just because you have an additive contribution, that's just one contribution. That doesn't tell you what the total is, okay? So for example, if we had a particle near the Planck scale, it would give a contribution to the Higgs mass of this size, okay? Now, I've given it to a ridiculous number of significant digits, and you may wonder, why did I do that? Well, because this number is kind of too big by about 30 orders of magnitude. And so there has to be some other contribution coming from somewhere else, I don't know where, and I need to subtract it, and it ends up giving me 125 GeV. So really, it only differs in the last few digits here, right? But all these other digits, so you would have to calculate, for example, the contribution of this to, I don't know, 10 loops or something to get this much accuracy. And every digit is needed to get the order of magnitude of the observed Higgs mass until you get to the last few digits, right? So this could happen, right? This is called fine tuning. It seems kind of implausible, right? It seems crazy, but in fact, if you do this, the theory is perfectly, the resulting experimental predictions are fine. You can just hide this in your theoretical calculations. No experimentalists need to know about it. You have good predictions. They can be extrapolated all the way up to the Planck scale, et cetera, et cetera. It seems perfectly consistent, but we believe that, if this particle is a physical particle, this contribution is a genuine dynamical contribution to the Higgs mass. There seems to be no reason why something else should magically cancel it to this incredible accuracy. It's a bit like a pencil walking into a room and seeing a pencil balanced on its tip. It is a consistent solution, at least in classical mechanics, but anyway, it's an analogy. But it seems very unlikely, and we suspect that there should be some sort of wires or something that we don't see that's explaining why this particular solution was chosen. Okay. So I think it is extremely motivated to ask, well, are there theories that don't have this unnatural cancellation, so-called natural theories. And of course, there are, right? And one of them is the great love of John's life, which is supersymmetry. I've also dallied with her myself over the years. And so what is supersymmetry? It's a theory that relates bosons and fermions. It's a symmetry. It's a symmetry that amazingly seems to relate things that apparently cannot be related, namely things with different spin and different statistics, right? And so, for example, at most direct relevance for this story, the Higgs, which is a spin zero particle, is related by the symmetry to a spin 1/2 particle called the Higgsino, okay? And if supersymmetry were an exact symmetry, the Higgs and the Higgsino would be exactly degenerate. They would have the same mass, okay? And the reason that this is a solution to this tuning problem is because for a fermion, like the Higgsino, its mass is protected from quantum fluctuations. Okay, this is just a fact about fermions. And because supersymmetry then relates that Higgsino mass to the Higgs mass, then there's no fine tuning for the Higgs mass. Okay, now I explained to you why quantum fluctuations cannot turn a massless spin 1 particle into a massive one, but I didn't explain it for fermions. So let me do that. So for fermions, the story is a little bit different. So for massless fermions, we have this time the helicity is a half integer because the spin is a half integer. So we have a plus half integer and a minus half integer massless fermion, and they're related by CPT, okay? But the new feature in the massless case here is not that the number of degrees of freedom is different. A massive fermion has the same number of spin degrees of freedom, but if the fermion mass vanishes, then the plus and minus helicity states are decoupled. They don't couple to each other, and we get a symmetry that basically counts for example, the difference between the number of particles, the number of plus helicity particles and the number of minus helicity particles. And this additional symmetry is so-called chiral symmetry, because it has to do with the handedness of the fermions. This symmetry is preserved by quantum fluctuations, okay? Okay, so this is a new symmetry. It's catnip for theorists, okay? And it does this thing in a very elegant way. It solves this, the problem of the quantum corrections to the Higgs mass. Okay. Now, supersymmetry, because it's a symmetry, it has to apply. In fact, it's a space-time symmetry. I think I forgot to say that. It's a symmetry associated with space and time. It has to act on all of the particles. So every particle in the standard model now gets a super partner. Okay, and the next most relevant one for our discussion is the top quark, a spin 1/2 fermion. Its super partner is a spin 0 scalar called the stop. Okay. And if supersymmetry were exact, the Higgs and the Higgsino, the top and the stop, et cetera, would all be degenerate. But to explain our world, we need supersymmetry to be broken. So we can have a mass difference between these states. And if we do, then we can go ahead, we can actually compute what the Higgs boson mass is, or at least its corrections due to these new particles. So the stop has to be one of these heavy particles that we haven't observed, right? This is very much an aspirational theory, but we can compute its effects as theorists and see what it does. And for example, the one loop corrections here to the Higgs mass give a contribution that is proportional to the difference between the stop mass squared and the top mass squared. And if you think about it, this makes a lot of sense because first of all, it shows that if we have exact supersymmetry, then this difference vanishes and we don't get any correction to the Higgs mass as we expect from symmetries, okay? On the other hand, if the stop mass is getting heavier and heavier and heavier, effectively at energies below the stop mass, we just have the standard model again, and we should expect quadratic. My previous argument said you should expect quadratic sensitivity to heavy particles, and there you go, right? If the stop mass is very heavy, then you get a contribution to the Higgs mass, which is proportional to the heavy particle mass squared. Okay, and we know all the couplings here. I've given this a squiggly. I've given this calculation at the squiggly level, but we of course know the precise coefficients, so we know exactly how big these contributions are if you know the stop mass. And there are a few other parameters that come in as well, but basically we know that, okay? And so if we don't want to have any large cancellation, okay, we know what this prefactor is, and we really do get that this scale is legitimately right around 1 TeV, where things start to get, where you start having to have very large cancellations, okay? So this is a very, very beautiful idea, okay? If it had been seen at the LHC, you would have heard about it, and so it wasn't. So there have been many, many searches at the LHC. What do they tell us? And the answer is that this is a very, very complicated question to answer, and I'm just going to punt on it. So, you know, the reason that it's complicated is because the bounds on new supersymmetric particles depend on precise details of how they decay. Okay, they can decay in stealthy ways that typically require particle masses to be accidentally close to, or maybe not accidentally, but requires unrelated particles, apparently unrelated, to be close in mass to each other, and so on. There are also additional sources of these fine tunings that I'm not even going to try to talk about. So I'm just going to just give a very, very, you know, sort of one sentence summary of the way I see things, is that, so experimentally, it is certainly still plausible to have m stop less than a TeV. You can see that on this slide, for example. This is a recent plot from ATLAS, and you see that the stop mass on the horizontal axis, there are still some regions up here where the stop mass can be below a TeV, but it depends very much on the mass of this neutralino, which is one of the particles that it decays to. And there's even more parameters hidden in this. So the story is much more complicated even than this plot, okay? But it really seems completely unavoidable to have anything less than 1% fine tuning in models that were written down ahead of time to not, you know, include every possible gadget to reduce fine tuning. The fine tuning is much, much worse than that. Okay, and this has made a lot of people a little bit bummed. As Guido Altarelli said many, many years ago already, the train of supersymmetry is late. All of this excluded region is region which could have discovered supersymmetry if it was some simple model, but it didn't. There's clearly a hint here, okay, as much as we might love supersymmetry. Another idea that I want to talk about, and these are not, this is the last one, and there are more than these two, but these I think are illustrative, and I think they're probably the leading contenders. The other goes under the rather technical name of pseudo Nambu Goldstone boson Higgs. Okay, so I'm not going to explain why it has that acronym, because I'm taking this rather ahistorical, I think logical approach, but that is the name of it if you want to Google it. And the starting point of this is the observation that the Higgs mass, the mass of the Higgs particle that we observe, is exactly related to the curvature of the Higgs potential. So remember, we live here at the bottom of this Higgs potential, and it's this curvature of this potential that is the mass of the Higgs boson. So if we want to explain a very light Higgs boson, what we want is a potential that is somehow very flat, okay? And what could make the potential more flat than just saying that, well, there's some symmetry, which is not going to be exact, but it's just like supersymmetry. It's this aspirational symmetry that might become true, or at least approximately true in some more fundamental theory, where the Higgs field can shift and nothing changes. Okay, that would be a symmetry that would certainly make the Higgs massless. It would make the curvature of the potential zero. It would make the whole potential zero. Okay. Now, of course, this is throwing out quite a bit of the baby with the bathwater. Okay, and in fact, just the ordinary standard model interactions with the Higgs break this shift symmetry. It is not a symmetry of the standard model. Of course, neither was supersymmetry, right? We had to add more stuff to make this an asymmetry, or at least an approximate symmetry. And the same story is true here. okay? So to make a long and very interesting story very short, you again require new degrees of freedom, and you can include those in a way that restores this approximate shift symmetry of the Higgs boson, okay? You need, just like supersymmetry, you need to enlarge the particle multiplets to have this be a symmetry. And in the simplest realizations, for the top quark, which gives a large contribution to the Higgs mass, you need a top partner, which is generally a fermion now, a colored fermion. And if you take its contributions, it also gives a finite, calculable, if you know the model, contribution to the Higgs mass. And again, it has this feature that if the new particle mass gets very heavy, then we're just fine tuning again. We're just having some heavy particle that the Higgs mass is quadratically sensitive to. But if we have a small enough value, if we have a light enough partner masses for these things, then we can cancel these large radiative corrections, and we have a rational explanation for the Higgs mass that we observe. Okay, and again, the LHC exclusion limits are around 1 TeV. It seems to be possible to write down somewhat less fine-tuned versions of these models. They have to be more or less contrived or something, but prospects look pretty good for finding a model with something like 10% to 1% fine-tuning. That would be my executive summary of this kind of approach. Okay. So this might be taken, and in fact, I take it as a hint. It's at least a hint that maybe nature is fine-tuned. It's at least fine-tuned a bit. It doesn't seem to be possible to write down a model where the low energy standard model just falls out, and if you just mess with the parameters a little bit, the predictions just change a little bit. There's no model like that. It does not seem to be possible. So there's some hint here that nature is telling us maybe nature is fine-tuned. And if we're going to take that seriously, okay, we should ask, are there mechanisms that might explain why nature is fine-tuned? And indeed there are, right? So we can imagine some kind of a cosmological adjustment mechanism. Okay, maybe the Higgs mass got somehow adjusted during cosmological history to be small. Okay, and there are actually versions of that. And another one is anthropic considerations. Okay, and maybe there are even crazier things. And I am going to take the plunge and talk about anthropics. Okay, it's a controversial topic. It makes some people see red. It makes it's kind of like this, graffiti of the anarchist symbol. It makes some people profoundly nervous, but I think it's something that we have to take seriously. So I'm going to talk about it for just a little bit. And the case for anthropics is that the standard model that we're also proud of and happy with actually has two tuned couplings. These are the couplings that it has that have a positive mass dimension. It has the Higgs mass, which I've been talking about this whole time, and the cosmological constant, which can be thought of as a contribution to the vacuum energy, which becomes relevant when we include gravity. And it's a fact, it's a scientific fact, that the existence of complex structure in our universe is also incredibly sensitive to exactly these two parameters, which are also the most sensitive to UV physics. Okay, this is just a fact, it's built into the standard model. So for example, if the Higgs mass squared was about 10 times or so, these are very, very rough numbers, larger than what we observe, we would have no stable nuclei. If the vacuum energy were about 10 times what we observe, we would have no galaxies. So the universe would be not just a little bit different, it would be radically different, okay? Certainly to a point where we could not imagine living in such a universe and observing it, okay? So how could this be science? I mean, this is a cool fact about the standard model, but you can't go in there and just change these couplings willy-nilly as far as we know. But the universe might actually do this for us because the universe may have completely causally disconnected regions, regions that we cannot observe from our part of the universe. And in these causally disconnected regions, these parameters might have different values. And if that was the larger universe, if we could zoom out and look at this larger universe, we would see most of it has no galaxies, no nuclei. And then there are these very, very rare regions where there are galaxies, nuclei, et cetera. And guess where we live? It's not a mystery. We don't live in those cold, empty regions. We live in the regions with complex structure. All right? That's the basic idea underlying anthropics. Now, this has very radical implications. You can ask, what can we predict? You know, can we really make sense out of this story? These are all very, very legitimate questions. But I think it is worth keeping in mind that it does not require any radical theoretical inputs. Okay, it just requires a lot of complexity, which in the potential energy of the universe, which string theory gives us. You know, tunneling gives us mechanisms to populate all these different local minima that would occur. It doesn't require anything exotic as far as the theoretical ingredients that go in, which I think is quite striking. And a lot of people, I think, including myself, would say that of what we know, it is the most conservative explanation that we have for the cosmological constant. There is therefore some kind of reason to think that this mechanism might actually be operating in our universe, whether we like it or not, okay? And so this kind of lets me, now you can understand, I think, the reason for my title, okay? Because we've been led down this path trying to understand this, the Higgs boson, trying to understand in particular its mass, has led us to at least two completely radically different views of the fundamental physics underlying our universe. In one possible universe, there's some new physics that has to be not too far from the TeV scale, probably with novel symmetries, and these give us a rational particle physics type explanation for why the Higgs mass is actually insensitive to UV physics, all right? Another possibility is that, sorry, the Higgs mass is sensitive to UV physics, and there is very high UV physics, and there is this fine tuning, but its value that we observe is explained, the explanation doesn't make sense unless you take into account our location in space and in time, okay? Maybe there are other possibilities. People are thinking hard. I'm sure I'm leaving out somebody's pet idea, but these are the most well-developed things, and this is what I see as being at stake in this kind of discussion. Okay, so how much time do I have left?
So we are around minute 40, so we are near the end.
Okay, I'm near the end too, okay, but I'm going to take a few more minutes, okay?
Okay.
Okay, so I want to now return to Earth. Okay, we have been in the stratosphere. So in the language that I've been using, this is very, very much aspirational theory, right? Trying to understand what physical principles might be there and so on. Okay, but you can see that it's a rather disconcerting, perhaps a bit disconcerting, right? How radical things are getting, how big the questions are being. So we should go back to Earth. Let's go back to the effective theory point of view. Okay. Is the particle that was discovered 10 years ago the Higgs? So I'm just going to repeat what has already been said before. The couplings are compatible with that of a standard model Higgs over many orders of magnitude. This is impressive results from the LHC. And but I do want to comment that measuring these couplings is not measuring parameters in the standard model, because in the standard model, these couplings that are being measured so beautifully at the LHC are already predicted to much higher accuracy than what they're currently measured and what they will be measured at the high luminosity LHC. Okay, that's because the standard model is a very constrained theory. The error bars here look small because they're on a log plot, but these numbers are predicted in the standard model with much higher accuracy than they're being measured. So measuring them is not determining an unknown parameter in the standard model. It's doing actually something much more interesting in my view. It's searching for new physics. It's searching for a deviation in the standard model, okay? And in fact, I want to underline this point. Any deviation from the predictions of the standard model requires new physics at a scale that we can calculate. So if you tell me, oh, what about this kind of deviation from the standard model physics, I can go away and calculate that with that deviation and no additional degrees of freedom, the standard model will break down at a high energy scale in exactly the way that these effective theories have broken down since the 1930s. Until we observe a deviation from the standard model, we can extrapolate forever, but as soon as we see any deviation, we can't extrapolate anymore, okay? And this scale at which the standard model breaks down for a given deviation, I think is a very interesting way to think about what is the significance of different measurements that are being done now, okay? So first of all, let me say, why is this true that any deviation? It's precisely because the standard model is the phenomenological theory. In fact, it is the most general theory of the observed particles that you can write down that has good high energy behavior. Okay, you can't, that is another definition of the standard model, okay? And so any deviation from it, the theory breaks down at high energies. It's as simple as that, okay? And so this is actually the only slide that involves my own work. So you can take the two perhaps best measured Higgs couplings, the Higgs coupling to W's and Z's, and the Higgs couplings to top, and you can imagine, what if there was a deviation? Given that deviation, I could predict the scale of new physics. What would it be? That's shown in this plot here, okay? So, and this right here shows the current, or maybe this is not the most recent, but it's pretty close to the current observational limits, okay, on these two couplings. And what you can see is that out in the outer reaches here, which is perfectly compatible, I can't remember, I think these are 95% confidence level, but I forget. Anyway, perfectly compatible with present measurements, you can have the scale of new physics at a few TeV, okay? Now the high luminosity LHC is expected to have an error something like this. So if the high luminosity LHC lands on the standard model, then we would have a much, much tighter constraint. But of course, we're all maybe secretly hoping that it will land out here, okay? I mean, it certainly, it certainly could, okay? And so what we can see is that we are still, in a sense, exploring the TeV scale after so many decades of, proposing the standard model and finding it in all of its details, including finally the Higgs boson. So my conclusions, I've tried to argue that the Higgs boson is really at the heart of some of the most important questions that we can ask in fundamental physics. These are true scientific questions. We have a hope of answering them. I think that further experimental study of the Higgs and going further into the high energy frontier are both essential if mankind is ever going to answer these questions. And on the theory side, I think we need to fire on all cylinders. We need both bold speculation, but also rigorous phenomenological analysis. And as John nicely reviewed, this is what got us to where we are now. We need to repeat this kind of cycle, right? And I'm very optimistic, and I think there's a lot of reason for optimism. Thank you very much.